Thanks, Erica. It's great to be back. I always enjoy this conference. I think it's one of the best in the industry. So thanks for having me back this year as well. So I'm Austin Federa. I'm one of the 3 co-founders of the DoubleZero project. Some context, I spent the last 4 years at the Solana Foundation working on technology and technology strategy there. Previous to that, though, I was at Bison Trails and worked on a bunch of the ETH to ETH2 staking infrastructure, beacon chain work, those sorts of things. So why do we need a new internet? Let's get into this. So what we are building is a new base layer infrastructure protocol and system. So it's a global physical fiber network for high-performance distributed systems and blockchain. And so I can't hit this enough because people still get confused. This is physical cables in the ground. We're not talking about software overlay networks. We're not talking about, other types of systems like VPNs. This is physical infrastructure for high-performance distributed systems. And this is kind of an alternative pathway for consensus, for state propagation, data delivery, MEV, RPCs, and it's using technology that is not available today on the public internet because the public internet was largely built with 20 to 30-year-old technology at this point. So here's just kind of a quick overview of my 2 co-founders. So Melbeck Labs is our labs entity. I am the founder at the foundation. These are entities that have always been separate, so it's kind of unlike a lot of projects where you have a split that occurred. So Melbeck Labs is one of the core contributors to the DoubleZero protocol, and Jump Crypto and the same team that built the FireDancer client for Solana are another core contributor group. So my 2 co-founders actually have no crypto background at all. They're both high-frequency trading and high-performance networking folks. So Andrew McConnell spent 18 years working in all sorts of parts of the stack. So that means from centralized exchanges to Jump Trading, building out high-frequency trading networks, sort of some of the fiber transition to microwave and shortwave technologies. And Mateo Ward, sort of a similar background, but more on the company formation side. And so these are folks who, one of the questions we get asked are by actual networking people is what do a bunch of crypto people know about building networks? And the answer is very little. That's what we have these 2 great guys for. So here's the problem with the internet. This is a graph over about 24 hours showing a ping time, which is a measurement of the latency between a server in Los Angeles and Singapore. And there's a few different numbers on here which are worth kind of paying attention to. The orange line and the yellow line are 2 alternative pathways through the public internet. So if you're just opening up your computer and you're trying to talk to another server somewhere in the world, it is not a consistent experience. As you can see, we start off pretty decent, 300 milliseconds or so, but there's a pretty fat band there. You see all that variance in time based on one ping versus another ping. This creates something called jitter. And people are really familiar with latency as a concept, but jitter is a measurement of how much variance there is between when you send a message and then you send a message a second later and a second after that and a second after that. So the public internet was never designed for high performance. It was designed for universal reach. And this is really kind of apparent as you can see through here. So you could actually see the moments in time when the internet service provider that we are measuring this against switches the cable, the physical cable under the ocean connecting Singapore and Los Angeles that they're routing you through. Because not all the cables are connected equally. Different performance characteristics exist on different ones. And you compare that to the blue line down at the bottom. And that's using our testnet, which is running on a piece of physical fiber between these 2 locations. And what you can see is it is consistent across the entire time base, irrespective of how much activity is going on, high periods of activity. And you can see there's a few moments on this chart where the internet actually beats our dedicated cable. It's not necessarily that the internet is always low performance, it's that it's extremely inconsistent performance. And you might think, why does that matter so much? Well, for the Ethereum L1 and for Bitcoin, it doesn't matter at all, right? You have 30 seconds to build a block on Ethereum, and 98% of that time is just to allow networking to occur. Only about 2% of that time is actually for execution or building a block. The minute you move into L2s, networks like Solana, networks like Sui or Aptos, the variance you get in terms of how long it takes data to get places is a major limiting factor in how fast you can actually run these validator networks. So like the Solana Firedancer client is a great example of this. We've run clusters that have nodes running in 4 different continents connected via the DoubleZero network, and we can run 1 million transactions per second. We can't get anywhere near that over the public internet. And this is part of why the journey of testnets to mainnet are usually so disappointing. Like some of it is people are just bad at benchmarking, but a lot of it is when you get into the real world, networking is a lot messier than it looks like in a laboratory setting. So what are we doing here, right? This is the OSI stack of the world, if you're familiar with this from computer science, and we've kind of stuck a bunch of other blockchain stuff on this as well. So we call DoubleZero an N1 because it is not a smart contract network. It does not have state. It is not trying to replace or compete with L1s. It's fundamentally a network architecture underpinning high-performance distributed systems. And so we're dealing with this very low level of the stack, layer 1, 2, and 3. Almost everything in blockchain is layer 5, 6, and 7. And so what this means is like DoubleZero can run underneath existing blockchain systems, and they don't necessarily even know that they're running on top of DoubleZero if they don't want to. There's a lot we can get into on optimizations there, but this is kind of like, we joke this is crypto's first infrastructure project, because everything else in crypto that talks about infrastructure is software infrastructure, and software infrastructure is super important. But if we actually want to make these systems compete with TradFi systems, we have to use the technologies that TradFi systems have. We have to make it cryptographically proven. We have to have economic security on it. We have to, do a whole bunch of other things to make it work for blockchain. But fundamentally, if we limit the performance of these systems to the internet, TradFi is going to run, loops around us, and even cloud providers will run loops around us for years and years. So what is the DoubleZero architecture? There's 2 main systems that go into this. The first is a global network of physical fiber cables contributed by independent contributors. And this is really key. All private networks that exist today, whether it's the one that Jump Trading or Citadel runs, or Google or Amazon or Facebook, are all run by one central single company, Facebook or Amazon or Google. In this case, we've designed a protocol that actually allows independent network contributors to mesh basically different pieces of fiber together. And so it appears to a system operating on top of the DoubleZero network like it's one cohesive high-performance network, but each contributor is in charge of their own boxes and their own fiber links. And so you have the kind of decentralization and security that you would expect from a network we're asking to carry blockchain traffic. The second part is we've integrated FPGAs in line with the network, and we can offload a ton of common tasks that people either have to spend a ton of resources on today, or quite frankly, go to someone like Cloudflare for to support. And so by implementing this in hardware, we can make this significantly faster. And the reason we're using FPGAs and not ASICs is the field programmable, right? You can reprogram FPGAs and you can't reprogram ASICs. Eventually, there may be ASIC applications here, but when we're dealing with blockchain, honestly, the data rates are so small nowadays that the performance of high-end FPGAs is more than sufficient. So what does this look like in practice? So this is kind of a conceptual model and also where the name DoubleZero comes from. So you have systems located outside of the DoubleZero network. That may be external validators or external RPCs. And they are able to communicate with validators that are located on the DoubleZero network. And sitting in between them is this filtration ring. But the filtration ring is not like a bunch of servers in between you and your transaction. There's a lot of networks like Qtum back in the day had this whole setup where you had sentry nodes outside of the internal network, and that was all to prevent like DDoS and attacks like that. Our filtration ring is implemented in hardware, and so it's extremely fast. You have no real additional latency in going through the FPGAs relative to just talking to a validator directly. And so we're able to basically offload a ton of the security that validators have to do. Not the crypto economic security, but things like preventing DDoS attacks, like making sure that they're prioritizing votes over other types of activities. So this is the fiber network. This is actually built out today. This is going to be our mainnet system. There's actually a bunch of links that are not on this map because the map's fairly old. But what you can see is we have multiple connections into the same geographies. And this is really important. So if you look at something like Tokyo, where a huge amount of stake for high-performance networks is run, there's 5 different independent contributor pathways data can take into that city. And so this is how you start to get private networking that can approach the decentralization of the public internet when you're looking at like a global network connectivity layer. And this is, again, this is all built out today. Our testnet incorporates some of this in it, and mainnet is coming in Q3, and so this fiber will be available for folks to use through that system. And this is all 100, or almost all of this is running on a 100 gigabit network as well. So we have huge amounts of data available. But it's not just about data. It's not just about filtration. There's a lot of other stuff that go into this too. So this is a simplified version of the architecture that we work on for DoubleZero. So if you're familiar with networking, a lot of these things are the same. There's a data plane, there's a control plane, there's a management plane. The difference is these systems are not controlled by one centralized entity. There's this DoubleZero network orchestration layer, network orchestration and DZ orchestration that go on top of it, and all of this rolls up to a DoubleZero ledger, which is, effectively under the hood, a lightweight blockchain. And so things like new routes proposed on how a packet will move from point A to point Z are actually reached in consensus on the network. That routing table is public. It is published. It is voted on, right? All of these types of things you expect from crypto are actually like part of the networking stack. And one of the really cool things here is we actually have a full IP address system that is all assigned by smart contract. There are no centralized controllers in the design of this system. Now in the testnet today, we have all the admin keys, of course, but this is the first time someone has really attempted to build this low level of a network system in a decentralized fashion while maintaining high performance. So let's talk about some of the technologies that are available on DoubleZero. And so the first one we talked about was filtration. And this uses FPGAs to offload common tasks from validators and create this protection layer. So if you look at high performance networks, a lot of what they do is not actually build blocks. It's prepare to build blocks, right? If you're running on Ethereum and you have a mempool, that's the function the mempool has. But suddenly, if you're looking at MegaETH, or if you're looking at Monad, or you're looking at Solana, the volume of incoming traffic and the latencies that users expect you to be able to deliver don't really allow for that type of architecture. So we can do signature verification in hardware via FPGA, right? This is 100 gigabits per second of line rate signature verification. So if there are 99.9 gigabits per second of fake invalid signature transactions coming in, we can sort through them and just let the good ones continue to pass through. Additionally, we can do deduplication of packets in hardware as well. So if you get the same packet, 3 times within a minute, it won't be allowed through. This makes it much more expensive for a DDoS attack to attempt to attack a validator because now they have to generate unique packets in order to try and get through that system. And so it reduces the cost, or it increases the cost of a DDoS attack significantly. Also, once you get up to 100 gigabits per second of DDoS, that's the data center's problem. That's not like the validator's problem anymore. You're going to be setting off alarm bells upstream from you. Your ISP is going to be calling you wondering what the hell's going on. It just changes the dynamics entirely from a you problem to an us problem. And that is really the goal of this. It's resource sharing to allow things to be much more performant. And one of these FPGA systems integrated into a switch can support numerous downstream validators from it. So it's not like we're asking every validator to go out and spend $10,000 on a bunch of FPGAs. We can have, potentially 100 different validators all sourcing data from that same filtration system. And again, this is a bump in the wire design, so we're not looking at systems that introduce additional latency in them. Going on to multicast, multicast is one of the coolest technologies that is not used in blockchain today, but should be. The problem is it's not available on the public internet. So if you think about what happens when a validator builds a block, it has to get that block out to every other node in the network that's voting, and every RPC server, and every indexer. And that takes a lot of time, right? If I have to go send out data one by one to 2,000 different nodes all over the world, that actually takes a meaningful amount of time, and it takes a lot of bandwidth. This is why Solana validators require such high bandwidth. It's also why sequencers, the RPC network around sequencers, is actually the hardest thing to support in most L2 architectures if you want timely, fast delivery of state updates. Remember, the RPC server is useless if it doesn't have fresh data, right? If your RPC is running 3 seconds behind where the chain actually is, on modern L2s, that is, 6 or more blocks behind where the market actually is. And so there's all of these data propagation problems that people don't really think about. Multicast is a hardware packet replication technology, and this is used in high-frequency trading firms all the time. It basically allows the validator to send 2 copies of the data out, an A feed and a B feed, and then the network automatically replicates those packets in hardware in the switch and gets them to everywhere else they need to go. And the cool thing about this is it's last mile replication. So if you're going from Amsterdam to New York and you have 10, or 100 validators on one side and 100 validators on the other side, it's only sending 2 packets across the wire. It's not sending 200 packets across the wire, and then they're replicated when they arrive at their destination. So it's a very efficient way to make sure you have high performance data and you have really low latency data as well. And we can segment this out by group, so you can get a multicast feed that's like all state transitions on Solana. You can get one that's all state transitions on Monad. You can grab another one that's all the Mega ETH state transitions, all the near state transitions. And this ability to segment and interoperate these things on one network, I think is going to be a huge benefit to anyone trying to run interop protocols or trying to actually watch state transitions across multiple locations. So yeah, the DoubleZero ledger, as we talked about before, this is basically a super stripped down blockchain. But the cool part is contributors, those actually providing fiber, they're authoring smart contracts that specify SLAs and specify terms. We also now have high precision on how much time it takes. So you can look at the routing map and say, I'm in Singapore, I'm trying to talk to Seoul. Here's the path my data is going to take, and here, with a very high degree of specificity, is how much time it will take for that to happen. You can't get this on the public internet, and you can't get this anywhere else at the moment. The ability to say with a high degree of determinism, this is the path it will take. As I mentioned, we also assign IP addresses based on smart contracts, which is just a very cool system, and one of the last pieces, even on the internet, that's a major point of centralization, is you're relying on centralized authorities for all of these types of things. We're also able to do prioritized routing, which basically brings characteristics similar to high-frequency trading firms to crypto. If you are a MEV system, if you are a professional trader, you can pay to make sure you're always running over the fastest piece of fiber between point A to point B. But in crypto, right, it's not point A to point B, it's point A to point N. At one moment, the validator you're trying to talk to might be located in Singapore. The next moment, it's in Johannesburg. And then the validator is located up in, Prague. That's a very complicated map to try and build out unless you have fiber into all of these locations. And so you can use DoubleZero as sort of like a hyperloop or a highway to jump onto it, go the far distance, and then you do last mile delivery outside of the DoubleZero network. And so we can bring things like zero jitter and predictable transmissions to blockchains for the first time. We also have something that no one thinks about, which is the internet can censor you. The internet does actively censor you all the time. It's possible to deep packet inspect transactions moving through any of these networks and front run, right? We don't think about this today as a major point of censorship resistance, lack of guarantee on the public internet, but there's no guarantee when you send a packet it's going to get delivered. It's not going to be withheld by a switch somewhere in the path, and they're not going to try and front run you based on the content of that packet. There's a whole bunch of things like this that you just can't get on the public internet, but they're not vulnerabilities that people usually think about. So we can also route around things like cable outages and provide transparency into where this is all going. So that's a pretty quick overview. I intended to leave some time for questions, but I think we're pretty close to the end on here. But But we are working with all sorts of different layer 1s and layer 2s and non-blockchain projects as well. So you can find more at doublezero.xyz and docs.malbeclabs.com. There's an email address there. As I mentioned, our testnet is actually up and running. We have about 40 Solana validators operating on it at the moment. Mainnet validators, not testnet validators. And we'll be launching the mainnet later this year. Thank you.